Okay guys, this video segment is going to start us off with the sample problems that we ended with on the last segment. We're going to walk through the different sample problems. I'm actually going to have you guys do these in class, and then I will go through each one of them to make sure that you understand what you did. And if you have any questions, then hopefully I'll be able to answer those as you are doing that. Okay, so the first question that we have is dealing with gas in a balloon. You have a set volume, you have a set kilopascal pressure, and assuming constant temp, what's going to happen to that volume of the balloon if we reduce that pressure? So that's what we're looking at in terms of our first practice problem. The second practice problem, if you take a look at it, talks about gas at 24 liters of gas, 175 kelvins. What will the volume be, assuming constant pressure? And then our third one, we have a rigid container, which means we have constant volume, and we have a temperature change within that one, or a pressure change within that one, and we need to solve for a temperature change. Okay, so we're going to pause the video now and have you guys actually work out all three problems, and then we'll go through the answers with you in a minute. All right, thanks. Okay, now that we're all ready, we will actually go through the different ones and make sure that we're all on the same page and that we can do these gas law problems. So in the first problem, we'll go to the board here, we're dealing with volume and pressure, and we're holding constant the temperature. So that is Boyle's law. So Boyle's law tells us that we have pressure times volume initially equals pressure times volume final, or ones and twos. We're given our initial pressure and volume, and we're given an ending pressure, so we're solving for our volume. So rearranging the equation, we're solving for this second volume here. We can say that P1 V1 over P2 equals V2. And now we're going to plug in our numbers for these values here. So initially we had a volume of 7.5 liters. So we have 7.5 liters. We initially had a pressure of 101 kilopascals. So 111 kilopascals times 7.5 liters, and we're dividing by a new pressure, our P2 of 45.0 kilopascals. And if we notice in our labels, kilopascals are going to cancel, so we're left with liters as our label. And now we just take 111 times 7.5 divided by 45. So 111 times 7.5 divided by 45, and we should get 18.5 liters is our answer here. Okay, so we get 18.5 liters. From the problem, we actually had 7.50 liters. That is why we still have three significant figures for this problem, because these are measured values. Okay. Again, Boyle's law, because we had temperature constant. So we're dealing with just pressure and volume with this one. Second problem. In the second problem, we have 24 liters of gas at a temperature. So we have a volume and a temperature we're dealing with. So that's Charles' law. And here, pressure is constant. Okay. So we can set this up and solve for this one. What would the volume be at 400 kelvins? So we're looking for this volume at 400 kelvins. So again, rearranging the equation, we have V1 times T2 divided by T1 equals the second volume. Our initial volume given was 24 liters. Our ending temperature is 400 kelvins. Notice how we are in kelvins here. Okay. We must be in kelvins to do this math. You have to be in kelvins, okay? It does not work, you will not get the right answer if you work in Celsius, because you need to be in that absolute temperature scale. We're at 400 kelvins here, and we initially started with 175 kelvins. So in this case, our kelvins cancels, and we can solve for our new volume, or V2. 24 times 400 divided by 175. And we get 54.9 liters for our new volume. Okay. Charles' law, pressure is constant, must be in kelvins to do this math. Okay. Our third question. Now we're dealing with pressure and temperature. So we're using Guy-Lussac's law. So we have our initial pressure divided by initial temperature is our final pressure divided by our final temperature. In this case, we have a rigid container. So rigid container means volume is constant in this process. And what temperature will the container burst? So we're solving for temperature in this case. So we're solving for T2. So rearranging this one is a little bit more challenging, but still should be algebra that you guys did as freshmen for the most part. So let's get temperature out of the denominator. So we're going to move that up here. We're going to move this down and move that over. So we're going to end up with a temperature 2 equals P2 divided by P1 times T1. Okay? So basically, we brought this up, brought that over, cross multiply, divide, and brought that down. So here's our equation. Solving for temperature 2, our second pressure in this problem was 100 atmospheres. Our initial temperature is 373 kelvins. Again, you have to work in kelvins. If I give you a problem in Celsius, and I will, you must convert to kelvins before you do the math. You can't convert after. It has to be done before any calculations are done. Okay? And our initial pressure that we started with was 25.5 atmospheres. Okay? So 100 times 373 divided by 25.5, and we should get a temperature of 1460 kelvins in there. Okay. Now I don't care. I always do my algebra, and with the letters in it. I've gotten used to doing that through physics and other things I've done in the sciences. I like to do my algebra this way first. I completely understand if you want to do this, insert numbers, and then do your math afterwards. People are more comfortable with that. That's completely fine also. But you'll always see me when I do practice problems work it out this way, where I rearrange the equation and then I solve for my my process here. Okay. So these are your 3 sample problems for each gas law. Hopefully you're going to find that these are not overly challenging math problems that we're working on right now, but they do kind of get more complex as we move on with the system.